Let me reintroduce Erran. So he's the chief scientist at Pony.ai, and he's also an adjunct professor at Columbia. So
yeah, thanks very much, Sujay. Thanks very much for inviting me. Sorry for the technical difficulty. I'm going to talk about the role of good old wireless communication networking in autonomous driving. Currently, when people approach the problem in the industry, we have all these sensors. You probably are familiar with the LiDAR sensor, and then you see the point cloud. And we have these sensors. We have to outfit them with a fleet. So right now we don't have really a good way of figure out when we're ready, so we basically go out and do extensive data collection and testing. We're using all these different sensors. The reason is that each of these sensors give us some piece of the puzzle, some piece of the information. It's mainly due to the limitation of current technology. We could actually drive with cameras, but the current state of the art of computer vision for stereo is, for 3D computer vision is not good enough. So that's why we also use LiDAR. LiDAR gives us very good depth information, but LiDAR also doesn't, has limitations. It doesn't give us very good speed information, so we have to rely on radar for that. I'm going to mainly talk about the challenges of applying machine learning to solve autonomous driving and how we can actually improve the system using wireless communication and networking, mostly for perception and prediction planning. At the end, I will talk about a new framework which considers wireless communication networking as an integral part of the system. If any computer vision people in the audience, the first thing you need to do in perception for autonomous driving, you need to do 3D object detection. And people may have worked a lot on the 2D object detection, but we have to operate in 3D, so we need to have 3D bounding boxes rather than 2D bounding boxes. And so we need to leverage both the depth information as well as the RGB information. And so to give you some ideas on what the community has been doing in processing all these sensory information for perception, and so there's some, as you can see, though, we have made a lot of progress, but you'll see that we are, far from solving the problem using computer vision. So one of the things is how do we actually process 3D point cloud data? And so, the first thing people did is just, okay, I can project the irregular 3D point cloud onto 2D, and then I can actually slice the height into different channels, and I can use 2D convolution. And then also people thought about, oh, I can just voxelize it using 3D convolution. But both approaches actually lose a lot of information during the quantization stage. And then be really interesting recent work on processing point cloud data natively without actually doing the quantization. And so the key motivation for this is that, for 2D images, and we're really processing very regular array of pixels, and convolution operation is really very good at extracting these deep image features. And for point cloud, actually, we have a different type of data, right? Essentially, we have an ordered set of points, and then we're interested in extracting these shape features or deep geometric features. And so we have to really find the operation that is actually good to process this type of data. And then, so very recently, this PointNet series of work has been pushing the frontier of extracting deep geometric features. So I talked about how to process 3D point cloud data, and then you probably have read a lot about all these companies that are promoting multi-sensor fusion techniques. And so really what people are doing is that, okay, I got these regular grid 2D images, and then I got 3D point cloud data. And what I'm really interested in are the bounding box I showed you that I need to output. And how can I actually leverage both types of information? And so people have done that naively by just shoveling RGBD data into a convolutional neural network. And then quickly people realize that's not going to work very well. And there have been some recent work which does a much better fusion, which you actually do 2D detection first. So you got the 2D boxes, and then that 2D boxes actually corresponds to the frustum of a 3D region, and then in that region you only have one object of interest, so you can just do segmentation. So you can actually leverage the advancement of both 2D detection and 3D deep learning to simplify your problem. And so even with the current state of their model, you see that there are cases where the blue boxes are where we don't have good detection. As you can see, those are to the right or here. There are two people side by side, and then one is, very occluded, and also here you got, very occluded, and then so if you couldn't detect pedestrians crossing the crosswalk where very close to the car, you're really in trouble. So that is the detection problem, and then we also have to track these objects in a over time, because we need to actually do prediction afterwards. And the dominant approach right now is common filter-based approach, and so we have to track their position, velocity as they move through the 3D world. And so this common filter-based approach is pretty good on a lot of cases. But there are a lot of other cases that it will fail, right? And so we have all these problems. How can we actually leverage wireless communication networking to actually, increase the reliability or the accuracy of our perception system? Well, one of the things is actually the sensors, right? So, LiDAR, for a lot of the good properties give us, it also have a lot of disadvantages, right? So you may not know that even car exhausts that you get LiDAR returns, right? And then you have to filter the the points that belong to car exhaust because you don't care about car exhausts, right? And then you also have mirror reflections, and then I also said it's hard to infer the speed and heading. So potentially, we can leverage a lot of the wireless communication techniques to create a better radar, right? Actually, there are startups actually in this space where kind of evaluating their technologies where you can actually make a radar that returns much denser point clouds, and much denser than the current radar, right? Although it might be still an order of magnitude smaller than the points you got from LiDAR, but radar actually it's not sensitive to the fog and rain, all these conditions, right? And then you could also leverage radar array to actually increase the reliability of the sensor. And so there are more than one startup that are working on this problem. And then come back to the perception problem. If we could have communication devices on these dynamic objects, and they can just communicate their position, heading speed, and bounding boxes, right? So, essentially we solve the detection problem very easily. And so also for the tracking problem, right? If we assign unique vehicle IDs or object IDs, and then we can actually associate them, very accurately. And But you also have the cases where objects may not all have the communication devices, right? So let's say if you have pedestrians or you have objects in occlusion, right? And then there, what we can do is we can leverage the detection of nearby vehicles or actually infrastructure, right? So there have been companies that are proposing that you actually, instead of outfitting the car with those sensors, you outfitting the road infrastructure, right? So, the good thing about outfitting the road infrastructure is that, you're looking down, right? So you have less of an occlusion problem, right? That is perception. Prediction, we have to recognize people's intention. We need to know where they're going to go, right? What is their future trajectory? And this has to be in a much longer time scale. And so that, we have to consider their past motion, the road, structure, and the interaction with other vehicles. And because we need to predict longer term, and then you have a lot of uncertainties, right? You have a distribution of possible outcomes, and then you don't want to predict a single outcome. This may not look very clear, but you see that at any given point, you have multiple possibilities, right? And then you need to predict all those possibilities that might impact planning. If you predict a single outcome, it will be the average. It may not correspond to any reality, right? And so the prediction problem is actually very difficult, right? And so for perception, you can actually transfer, from one region to another because you're dealing with perceiving the physical world, right? And the car will, look the same no matter where you go. But for prediction, is really people's behavior. Different regions have very particular behaviors, right? That for these agents. One of the things, for example, if you're coming out of a highway, right, and if to your right, if there is a large vehicle, and a lot of times this vehicle is not going to be staying in the middle of the lane, right? It will probably cut into your lane, and then you have to learn all these behavior from the data, right? So to give you an idea that some of the test cases we see in China, so here you got a cyclist that's actually riding in the reverse, and then we have to actually detect and then nudge over the cyclist, right? And then here you see that, this car that's really aggressively kind of into the self-driving car, right? So these are just some of the hard cases. There, as you might imagine, there are so many such hard cases that, really pose a problem for prediction. And then even the best machine learning model these days, right? So here's one, machine learning model that for the prediction problem. So, for those who are really interested in the machine learning side of the prediction, to give you a high-level idea, so you encode your past motion into a, vector, and then also your future, right? You know the future in training, and then you have these vectors. And then, you also want to learn the uncertainty aspects, right? So you got a multiple outcome. So you have to learn a conditional variational autoencoder in the sense that by sampling the latent code, for each sample, you can generate a future outcome. And, together with the latent code and then your current state, and then you can do the decoder, which is reconstructing your signal, right? And then you could also be more sophisticated, taking into account, the road structure and the interaction with other agents to further improve it. And so that's just prediction. And then planning, you have, so many problems that interacting with other humans, right? How do you model other agents, right? How do you handle uncertainty, right? And, can we actually learn a policy through imitation learning? Or, how much can we rely on model-based RL, right? And so there have been some recent work on model-based RL. And so you can learn a predictive model. So You can encode the state, right, using a context image where it's actually very abstract. You have cars that's in different positions, and you also have the velocity and position of the self-driving car. That's your state, and then you're going to learn an action, which is going to be the acceleration and steering angle. And your cost is some differentiable cost that, say, proximity to other cars. And so, like, this is, the predictive model of RL. So you essentially given the past state and then action, you want to predict the probability of the next state. Given this forward model, and you can actually learn a stochastic policy. So your policy just maps the state into actions, and then you have multi-step costs, and then you backprop, and then you're going to learn this stochastic policy pi. And so, but, the amount of scenarios can handle is still, pretty limited. How can we actually leverage wireless communication networking? Prediction planning is kind of intertwined. You can actually push the difficulty into prediction, and then planning is going to be simple, right? And so for prediction, if you have actually communication devices, you can actually just, send your steering angle and acceleration to other cars, right? And if you can send it much faster than the car can respond, you more or less can have actually very perfect predictions, right? But there are cases where you have objects that doesn't have communication devices, and then you would rely on cars nearby or infrastructure, right, to actually do much better prediction. And so these are just some of the ideas. How do we actually create a framework with wireless communication networking as an integral part? And so we already have connected vehicle standard DSRC, which already have messages that transmit positions, steering angles, right? And these, which is great. And so we need to go one step further by actually considering the these V2V and V2X in the context of the self-driving system, right? So standalone self-driving system is like this, right? You take local sensor data, and then you also take the map information, and you do perception and then prediction and planning. You can actually add the information from V2 and V2X into these components and increase your accuracy and reliability of the whole system, right? And so the main idea is to actually, through this sharing of information, which is much harder to get it right in a lot of the cases. And then the main challenges are, how do you handle imperfect perception output from other vehicles or road infrastructures, right? And which one do you trust? How do you fuse them? And if you do need some raw data, how do you selectively communicate these raw data, right? And if you need to take into account planning decisions of other vehicles, and how do you handle that, given that planning decisions change very rapidly? And so there are also a lot of the challenges are kind of non-technical because, how do you guarantee data quality is kind of decentralized system. Where is the trust, right? And then you got a whole bunch of issues. Finally, a shameless plug, and we got this research institute going on since May, and we're actually pushing the state of the art of AI. And so if anybody has students or is interested in full-time or interns, can contact us. So that's the end of the talk. Yeah, thanks.
Does anybody have any questions?
I hope I didn't miss it, but have you considered with so many pedestrians and more even like scooters and bikes and stuff you see around cities being connected to the internet, have you considered those objects being able to communicate with the vehicles? You know, a person crossing a crosswalk, you know, may be able to identify or communicate their position to vehicles around them.
Yeah, if those has communication devices, if they actually transmit, you know, their positions, right, that will be actually, yeah, help a lot, yeah.
I have a question.
Yeah.
So for autonomous driving,
Yeah.
Is there an industry consensus around, you know, having a car being able to drive without ever communicating with anybody else? Or is communication a vital part of autonomous driving?
Well, I think different companies have different views. So right now, I think most of the companies actually are pushing solutions that's, you know, that independent, you know, the independent vehicle has to handle all the situations. So there are a lot of factors. For example, it really depends on, you know, the industry want to solve this probably in 5 years. So, you know, if for a lot of these communication-related stuff, you know, it's very slow in terms of standardization and adoption, right? So if you couldn't have it adopted in, you know, say, I don't know how many % of the cars, and it really doesn't really help a lot, right? So, you know, the key is that you have, you know, almost complete coverage, at least in a lot of the settings, right? For example, you know, in certain, say in highways, right? If you have all the cars, all the vehicles that have this capability, that will, you know, solve the problem for highways. But if you have a mixture of cars, which a large fraction doesn't have the communication capabilities, right? And then, you know, it will help, but it's not clear, you know, whether it's gonna be, you know, crucial. Yeah. Yeah.
Any other questions?
So you started with the assumption that we need 3D geometric representation of 360 degrees. So why that is critical? Like, because we are driving with our eyes, so we don't need 3D information, but we have other models in present. But why that is critical for...
You were saying we meaning like humans.
Humans.
We have 2 eyes. You know, we do perceive things in 3D, right? So that, you know, we're using, you know, 3D information, right? It's probably not in the same representation as, you know, what in the current technology is using, right? So, you know, like, you know, as an engineering problem, like, you know, we have to measure all these, you know, in very accurately, very accurately, so that we have mass to handle it, right? So, you know, there are cases where we don't need really accurate centimeter accuracy. It's, let's say, beyond, like, say, 100 meters, right? But, you know, we have to be able to have a framework to handle inaccurate depth information, yeah.
Okay. So please let's thank Erran again.